Thank you, Louis and Tom. Hey everyone, I'm Gusso. I'm a designer on the design systems team at TransferWise. And I think my talk is going to be around 20 minutes, so we might have a few minutes for questions at the end. So if there's anything during the talk that you want to ask, just put them in the chat and I can answer them later. So a few months ago, a friend of mine was telling me about how he creates color palettes when starting a new project in Figma. So he would start by drawing these rectangles of the base colors that he was starting to work from. Then he would draw a bunch of black and white circles for all the shades that he wanted of each color. Then he would change their opacity to different values to blend the colors with the background and define all the intensities he wanted. Then he would use the color picker to sample the result of each of them individually and then create one color style for each on Figma with their names. And it seemed like a very manual process for something that he could visualize on his head when he was starting the process, right? And at that point, I've been really into Figma plugins. I couldn't shut up about it, but I still had made only one plugin and a couple of private ones for TransferWise. So I thought that this is a good opportunity to automate something and create a new tool. So then I started diving into colors to figure out how I was going to do this. But the thing about going from coordinating your hand movement with what you see on the screen to select colors to automating it with a tool is that you need to start describing colors as numbers. And the more I dug into it, the more I realized that there's a massive world of math that goes into creating and describing colors on displays. And it's quite broad and honestly quite intimidating. But I had the objective of creating the plugin itself. So my goal was to go only as deep as I needed to create the tool that I wanted to make. So let's start with how colors are displayed on monitors. Most monitors use a combination of red, green, and blue, very tiny light sources. This is a microscopic photo of an iPhone screen. And these lights are set to different intensities to display all the different colors that a monitor can show. So for example, if we take this blue color and we look at its representation in RGB, we see that it's a combination of the RG and B channels, red, green, and blue. And you can see, for example, that the blue channel is higher than the rest. So it makes some sense that this is describing a blue color. But for example, if we wanted to desaturate this blue, if we look at the difference in the RGB values between them, there's nothing here that tells me that the original color is more saturated, right? You have the green and red channels a little bit higher and the blue channel a little bit lower, but I wouldn't know that I would need to switch those numbers myself. And those numbers don't matter that much when you're picking colors on a color picker, because if you wanted to get a less saturated version of a color, you can just look at a screen and click on it and you would get it. But if you're describing in code, all you have is numbers. So RGB is not really intuitive to describe colors here. Fortunately for this, we have HSL that was created exactly for this reason, so that we can describe colors in a similar way that we think about colors as humans. So when we think of the color yellow, our minds don't think of it as a combination of red and green, right? You describe it first by the color that you learned it to call that color, right? And that's what we call hue. Hue is what defines if something is going to be red or purple or orange. The second channel, S, is for saturation, which defines how colorful, how vibrant that color is. And the third one is lightness, which defines how light, how close to white that color is. And this feels like a much more natural way to talk about color and to manipulate it with code as well. So when we look back at that desaturated blue, if we represent it in HSL, we see that the numbers make sense now. I am manipulating the saturation channel, reducing it by 40, and I understand that the way to get a less saturated color is reducing the saturation. And this is the goal, right? In this example, we use for saturation, but on our tool, we want to manipulate the lightness level and create all those 6 shades from black to white of that color. So let's say that we wanted to get 12 colors across the whole color spectrum and generate 6 levels of lightness for each. This is what you'd get with HSL. And looking at these colors next to each other, we might think that they have similar levels of intensity because we're probably quite familiar with them. HSL is pretty much everywhere in color pickers. If you picked a color in most pieces of software, you've interacted with some version of HSL. And like I said before, each row represents a constant level of lightness. So if we isolate the third row, for example, I'd expect to be able to use this color in similar applications. And initially, they might look similar in terms of how bright they are. But if we apply them to something that requires a bit more interpretation, for example, text, you might start noticing that there's a wave. Especially if you squint and look at them, you start seeing that some colors are brighter than the others. You sort of see a wave. Now look at the yellow and blue together. Like, imagine the confidence of HSL to look us in the eye and describe these two colors as having the same level of lightness. If you have a perfect vision and your sight is really sharp, you might ship products that are not accessible because you just believed on the lightness level of this color model, which is not very accurate. And I knew this wasn't right, but to find a way to fix this, I wanted to understand what is the problem with HSL. Why is it like this? And it's related to what light is. And I don't know if you know what light is. I thought I maybe sort of knew, but I actually didn't. I needed to research. So light is a range of frequencies of electromagnetic radiation. And there are tons of ways we know uses of electromagnetic radiation in our lives. You have microwaves, for example, which are the frequencies used by Wi-Fi, radio waves, X-rays, and we can't see any of those, right? We can't see Wi-Fi. And light is the range that we can see. Light is the range of electromagnetic radiation that we can see. And here in this graph, we see the relationship between the range of frequencies that we can see, which is from around 400 to 700 nanometers, to how sensitive humans are to them on the y-axis. And color is simply our interpretation of these wavelengths. Color is our interpretation of light. So if we plot out the color spectrum here, you can see that the blues and reds are on the far ends of the frequencies that we can actually perceive. And around the 550 mark there is where we're most sensitive. And this is the wavelength that we perceive to be as the greens and yellows. And this is what's being exaggerated by HSL, because HSL is a simple conversion of RGB, from what is actually being emitted on the monitor. It doesn't take into consideration how differently we perceive red, green, and blue to be. So when we look back here, we can understand why the greens and yellows are so brighter, because HSL doesn't treat them as differently. But for us, they are different. So we need a color model that takes into consideration that we don't perceive all colors the same way. And there are several color models that I could try, but I needed to find a way to compare them, because if I look at this, now I'm only judging these colors using my eyes. I'm not sure about like what are the biases in my own vision. So I can't trust that that's very accurate. And the W3C has a solution for that. So W3C is a community that develops web standards, and their accessibility guidelines has a calculation for relative luminance, which became really popular as the base formula to create the calculation for contrast ratios. So any contrast ratio checkers, if you used any tool that has a contrast ratio checker, you've used the calculation of relative luminance. And that's exactly what we want. So if you go back to this yellow and blue that we perceive to be so different, and they have the same lightness value levels in HSL, and we calculate their relative luminance, you can see now that they're on the opposite sides of the spectrum, right? Yellow is at 93% and the blue is at 10%. So what I'm going to do in the next few slides is start using these contrast circles on top of these colors to represent how bright we perceive them to be according to relative luminance. So on the yellow, you see that it's very close to the top, and the blue is very close to the bottom because it's a low relative luminance. So if you go back to the HSL graph and we put those circles there, we see that the rows are not really linear, right? So you can see that there's a big jump from the orange to yellow. And if we connect those dots, it becomes even easier to see. Now we are seeing the waves that we noticed when we squinted looking at those pieces of text, right? So now we know how to represent if color model is perceptually uniform or not. So, okay, now we're ready to test other color models. So one of the most popular perceptually uniform models is CIELab. And the good thing about lab is that the L describes a level of luminance for each color. that matches how intense we perceive it to be. So that's great, that's what we want. But A and B control a mix between green and red and blue and yellow. So this starts moving away from the way that we think about colors. I wanted to find something that matches more closely how we talk about things. So the CIE also created a similar one around the same time called LUV, but it had another problem, which is changing the values of a channel influence the possible values of the others. So you needed to do also a lot more calculation that I wanted to. It's not very easy to use in code. I wanted to find something else. So in 2012, a guy called Alexei Boronin launched HSLuv, which is a color space that uses the perceptual uniformity of LUV with the convenience of HSL, because you also control hue, saturation, and lightness. And I think that this is pretty much what I was looking for all along. And because it uses the same values, it's super easy to generate a similar palette to this. I can just replace it with HSLuv. And this is what it looks like. So this is much better already. We can see within the rows that the colors look way more uniform. And if we measure those colors' relative luminance, we also get perfectly horizontal lines, which means that the relative luminance in every row is constant, which was a big victory. For a moment, I thought I cracked it. But if we isolate the first row, you can see that the problem still exists. The greens are still more intense than the blues. And if we look back at the relative luminance, they are almost all exactly the same. Even the tiny variation between them doesn't really reflect how differently we perceive them to be. So it turns out that we can't trust the math for relative luminance either. The contrast ratio calculators that we use, they don't really take into consideration everything that influences how we perceive colors to be. So using this to measure colors becomes a bit hard. But the problems with current calculations have been noticed by a bunch of other people also. And since June last year, this color scientist called Andrew Sommers started working with the W3C to figure out a new calculation for color contrast. And there's a really good GitHub issue for this. I'm going to show a link for it at the end. But here's a good example that he gave. On the top, if you measure that violet text on top of white, it fails the W3C's accessibility guidelines, while the gray on top of black passes with a very big difference. The gray on top of black is 4.1 and the violet is 2.9. So it's easy to see that we perceive the violet a lot more, right? So sometimes the math and the contrast ratios is just very, very wrong. So Andrew's developing a new algorithm he's calling SAPC to calculate contrast ratios. You can follow his progress on that GitHub issue. But his goal is not to change the relative luminance, which is what we've been using here. He just wants to create a contrast ratio formula that takes into account more aspects of how we perceive color contrast. So that's something that I think we could use to calculate the ratios to create better palettes also. So I'm very interested to see where it's going to go. But it's not really ready. There is a work in progress calculator, but it doesn't take into account hue very well yet. So what do I do now? At that point, I had made peace that using relative luminance as a way to check colors was good enough for now. It's better than only my eyes. It's the standard that we all use. And I think I had learned enough to understand the current constraints of perceptual color models, while I leave all the math color people to figure out the complex calculations of the new color contrast formula that we're going to use in the future. So I was going to get back to finding the ideal solution for the tool I wanted to make. So the closest solution I had gotten until then was HSLuv, but I wanted to give a shot to its sibling, HPLuv. And this one is quite a bit closer to what we wanted because it's perceptually uniform all around, right? You can see that there's no more screaming yellows anywhere. In every row, things seem quite consistent. And also, if we take its relative luminance, everything is consistent. But you can see that it's restricted to pastel colors. And the reason is that the color space eliminated all colors which didn't have perceptually similar lightness equivalents in all other hues. So, for example, the really bright yellow that would always end up winning when fighting against other colors was cropped out. So this model worked, but I still wanted to see if I couldn't find something that did allow me to have a bit more saturation. And then I found out about Cubehelix. So Cubehelix is a color scheme that looks a little bit similar to HPLuv in terms of intensity. And it was created by this guy called Dave Green, which is an astrophysicist that wanted to use colors in astronomical photos in a way that the increase in intensity was visible both by hue and by bright we perceive it to be. And the reason that it also works well for creating palettes is that you have control over the distortion. So here you can see that at 100% saturation, the relative luminance is a bit skewed towards the greens, but not too much. But we can increase saturation above 100%, and the distortion increases, but a lot of the colors that we might be looking for come back. And if we keep going up, we can still see more vibrancy. And this is the beautiful thing for me. I think that Cubehelix exposes its constraints and weaknesses in the numbers it uses, right? It allows the consumer to decide how to use them. Because if you think about a palette at 200% saturation, it's easy to understand that you're deviating from what makes colors uniform, right? So it gives you the freedom to do those decisions by yourself. So this was it. I found Cubehelix to be the best tool available to create my generator on top of, so I was ready to put the plugin together. So I called it palettes, which I know is a little bit boring, but I wanted to feel as home as it could be on Figma, like a Figma feature. And the intention is for it to feel like an extension of the properties panel to manage groups of color styles together, which are our palettes. So you start by creating your first palette by clicking on the plus button. And then you get to the edit panel to define your palette. You type the name of the color you want, and you change the hue to be what you're looking for. And in the meantime, all the color styles are being updated live on the right. And then you go back to the list of palettes. You start creating a few more. And you start seeing that the plugin always shows you a live preview of the top of all the palettes you're creating, so you can see how they work together. And you can also control how many steps you want, and it updates the preview and the styles live. But let's say that you wanted to create a yellow. So palettes aims to be perceptually uniform by default, like Cubehelix aims to be. And we saw that the really bright yellow don't really match with the other colors. But if you have a situation where you do want to deviate, where you know what you're doing, you can do that. So even though the saturation slider is already at the far end at 100%, you can still use the numeric field to go up to 300% and increase the saturation further. So you can use colors that are not possible on the normal range. So this gives you that, that freedom to deviate and really know, allow you to do everything that you want, but also by default being accessible and uniform. So the tool ended up using the Cubehelix color scheme. The steps are all equally spaced. The naming scheme of the styles is all fixed. So I think that there's a lot of room to extend these functionalities to make it broader and appeal to more use cases. And I plan on doing some of that. But palettes also aims to fix a very specific workflow. And there are quite a few web tools that give you far more control for the palettes that you generate. So Colorbox, for example, was one of the first tools that really made me want to understand more about color palettes and color uniformity. And it was created by the design team at Lyft. And they give you a lot of controls for what happens in every step, how far the steps go. It's really good. Stripe also made their own tool to create their palette, along with a very good blog post that describes how they navigated the CIELab color space. That is crazy. Like, look at those graphs. Those graphs are describing the impossible colors in CIELab so that you can only create colors that do exist. It's insane. Unfortunately, they didn't release it, so that's not a tool we can play with, but hopefully we can see some version of it online someday. And Nate Baldwin, a designer from Adobe, created Leonardo, which is another way of creating palettes focused on showing you the results with UI for you to actually preview how a palette would apply to UI and charts. And it's also really good, open source. Anyone can play with it. It's great. So that's it. I added links to all tools I showed today on this website here. Also, there's a link to palettes and also a bunch of the references that helped me learn all this. If there are any color experts out there watching, I know that you have Jamie Wong on Figma that wrote a really good blog post on colors that helped me learn a lot. So sorry if I butchered any term here. But yeah, thank you.